Because we ran out of time in class during this power transmissions video or lecture, I just wanted to finish up. So we had talked about the pitch circle. Pitch circle was the circle right here, and that's the circle that the two gears will rotate as if they were friction drums with the pitch circle diameters. So anyways, you have your addendum circle out here, your dedendum circle down here. The base circle is the circle that is used to generate the envelope curve, and the base circle may be smaller than the dedendum circle, or in this case you can see it's larger than the dedendum circle. And so this part of the gear would just be a straight radial line, and then it would begin to curve with the involute curve right here. This line of action is as the gear teeth start to mesh, that's the point of contact between the two gears. And the pressure angle is the angle, if you look at this horizontal line, the line that's tangent between the two pitch circles here, right? And then you look at this line right here, which is then tangent, passes through that intersection, but is then tangent to the base circle. So that's how the pressure angle is defined. And so we have the distance between the centers, we talked about that, point of contact, and the line of action, pressure angle, pitch circle, pitch diameter. And so we also talked about finding out the distance between the two centers. By the way, the pressure angles commonly are either 20 degrees or 14.5 degrees. And let's see, so we went through this stuff. Typically the stage is about 95% efficient. And so then the next thing we want to talk about is these worm gears. And the worm gears, so they're usually very inefficient. They have the advantage of, especially with a shallow helix angle, that it's hard to backdrive them, so they're anti-backdrive. And in terms of the efficiency or the speed ratio, if you have just a single thread, which is, say, like, typical threaded rod, the thread starts just in one spot, right? In this particular picture right here, it actually starts in 4 spots. So if we want to know the ratio, it would be 4 divided by 50, right? If this gear right here has 50 teeth, if it only had one, if the thread only began in one spot, then one revolution would just move you forward 1 pitch. It would just, in other words, move 1 tooth forward. So in that case, for instance, then the speed ratio would be 1/50. Okay, and let's see. So they require you have to be really supported, and they don't transmit power very well because they're so inefficient. But you can get a very large ratio in a small area, and again, they have the anti-backdrive characteristic. So this is what we're talking about with a single start. You start on this side, and by the time you wrap around and come across, you can see that you move forward. The lead is equal to the pitch. So the pitch is the distance from one tooth to the next tooth, the same spot on one tooth to the same spot on the next tooth. So with one thread, as you rotate 360 degrees, it's going to move 1 pitch. If you have a thread that starts on either side 180 degrees apart, then this next thread here is not really from this particular thread. If you follow this particular thread around, comes back over here. So now in one revolution, you can see that you actually move the distance of 2 pitches and so on. So that's how when we looked at this ratio right here, the number of leads on the worm tooth divided by the teeth on the worm gear. So that's where this comes from right here. So here's an example with a shallow helix angle. So in other words, by trying to rotate this disc right here, it's going to be very difficult to try and move this the worm right here. Whereas if you have something with a really large helix angle, then you will be able to back drive it. Okay, so next we want to talk about chain sprockets and the chain number. Let me just get this out here. So this first number, the first digit, is the pitch in inches. So the pitch, we've talked about, pitch on a bolt, like a quarter 20 bolt. The pitch is the distance between the threads. So the 20 means 20 threads per inch. So the pitch would be 1/20th of an inch. And then on a gear, we generally talk about diametral pitch, which is the number of teeth per inch of diameter. So that's different than the pitch on a threaded rod. And now in chain, the pitch is the distance from center to center on the rollers, right? So ANSI 25 to 2 means it's 2/8. So the distance on ANSI 25 chain is a quarter of an inch between the pins. ANSI 35 is 3/8, which is not 0.350, right? It's 0.375. And the second number, 0 means roller, 1 is lightweight, bushed is 5. So ANSI 25 and ANSI 35 chain do not have the rollers, but they just have bushings here. And so this is, of course, the strength of the chain is going to depend on what material it's made out of. So obviously plastic chain, the VEX plastic chain is not going to be as strong as steel chain, and even steel has different grades of steel. So but typical, the typical steel chain that you buy from like MasterCar or something, these are typical numbers. So 875 pounds to break it, 140 pounds for a continuous working load. So obviously if you have something that you want to run for 10 years, you don't want to be designing it so it's really close to the braking strength. And then ANSI 35 is 2,100 and 480 pounds for the working load. So, okay, then we have links. And generally you want to have an even number of total links in your length of chain so that you can use this type of master link. So in other words, you're going to have 2 inner links and then 2 outer links and then 2 inner links and so on. So this distributes the load better. If you have an odd number of links, then you have to use these half links. So you can see that on one side it's an inside link and on the other side it's an outside link. And trying to transmit tension through this instead of through a straight piece like this, through this offset, obviously puts more stress on that. And as a general rule of thumb, if you use a master length, that link will only be 75% as strong as the rest of the chain. And if you use this half link, it's 65%. It also is more likely to jam. So generally, if whenever possible, you want to design so that you have an even number of chain links so that you can use this type of master link rather than the offset type. Okay, and here's a couple of other rules. Generally you want to stay above 12 teeth. The ratio, usually keep less than 8:1. So if you need, suppose you need a 12:1, so you might decide to do that with 2 stages. Another thing is you want to have 120 degrees of wrap. So in other words, on the pitch circle would be the circle that's drawn through the centers of these rollers, okay? And so by the way, if you know how many teeth there are in a sprocket, so for instance, suppose you have a 12-tooth sprocket and you have 1/4 inch chain, right? Then, so in other words, you're going to have 12 of these times 1/4 of an inch, right? So that's 3 inches. That would be the distance all the way around, the circumference. And then of course the ratio between the circumference and the diameter is just pi. So you could just divide by pi. That's gonna give you the approximate diameter, because remember that the chain doesn't really, the circle is passing through the pins, but the links themselves are like chords on that circle. So that's going to give you a diameter that's a little bit smaller than the actual diameter. And we'll get to how to get the actual diameter in just a minute. But anyways, for this gear right here, or the sprocket that's driving the load here, you want to have at least 120 degrees of wrap. So in other words, if this was 120 right now, if you move this closer, then it would be less than 120. And if the two sprockets are the same size, then obviously they would have 180 degrees of wrap. Or as the sprockets get further and further apart, then the angle starts to approach 180 degrees. But you always want to have at least 120 degrees of wrap. And so you might have to add idlers if necessary. So, all right, so this company right here, Stock Drive Products, Sterling Instruments, so you can go to their website, and there's lots of catalogs where they'll tell you the pitch diameter. Again, that's the diameter of the circle that's passing through the center of the rollers. As the chain sits on the sprockets, the rollers, if you drew a circle through the centers of the rollers, then you'd get the pitch diameter. And the outside diameter, of course, is the actual diameter out to the top of the teeth, top of the top lane of the teeth. Okay, so here's a couple of survey questions that you can take a shot at answering. And try to do this before class on Thursday. So here's two of them right here. One is what is if two sprockets have outside diameters, these values right here, what is the minimum center to center distance to avoid tooth interference? And then this one is if you have these two pitch diameters, what is the minimum center to center distance to avoid a wrap angle less than 120 degrees? Okay. And this equation, if you have two sprockets of different size, then you can use this equation, which relates the length of the chain to the center to center distance. So like if you didn't want to have any kind of idler or adjustment, and you wanted to have the chain fit exactly on two particular sprockets, then typically what you would do is first figure out approximately what the center to center distance is that you want. Remember, it has to be larger than these two minimums, right? You have to have at least 120 degrees of wrap, and you don't want the sprocket teeth to be hitting each other. So you would pick some center to center distance. Of course, usually you don't want this to be bigger than it needs to be, because then your mechanism has to be bigger. You need more space. But anyway, so you put in the value, just a ballpark value, and then from this equation you can calculate the length. But you're going to get some decimal number for length, and the length of the chain, remember that you want to be evenly divisible by the pitch, but even better by twice the pitch. So in other words, like ANSI 25 chain, you want that to be divisible by a ½ inch, the length evenly divisible by a ½ inch, 2 pitches, right? It's $1/4 pitch, and that's so that you can have an even number of links. So once you have that length of chain that's close to, you can normally round up. So in other words, you put in the C that you want, you get the L. Now you got to get the L, change the L so it's evenly, so it's divisible by 2 pitches. And now that you have the length of the chain, then you can go back and actually solve for the actual center to center distance. So get this very accurately. Steel chain doesn't stretch very easily, so you want to make sure that you get this number. Usually you want to get it to, if you can get it to 1/1000th of an inch, that's good. But you don't want to have it to, say, generally only 1/100th of an inch or something like that, or 10/1000ths. That you might have some problems. You don't want it to be the centers to be too far apart, so you can't get the chain on, and you don't want them to be too close together so that the chain starts skipping. But anyways, so this equation, you can set this up in an equation solver. Notice that if you have the C, then you can just put the C values in and calculate L. If you have the L and you want to calculate C, then you got C in the numerator here and the denominator here, so it's a little bit trickier. You can set up a quadratic equation and then solve for C with a quadratic formula, or just use an equation solver. Something probably on your calculator or in MathCAD, something like that. Okay, and then the other thing is, in the catalog, you can just look up the pitch diameter and the outside diameter normally, or you can use this equation where the little p is the chain pitch. So if it was ANSI 25, you'd put in 0.25 right here, and then this is in degrees. So if n is the number of, n would be the number of teeth on the sprocket, 180 divided by n, and that's in degrees. Take the sine of that, and then you can calculate the pitch diameter with that equation. Okay, so for planetary gears, if you go to the slide set here and click on this link, you'll get a really nice animation that will allow you to visualize, changing the size of the pitch diameters of the planet gears. This is the ring gear out here, and here's the sun gear in here. And so if we have time later in the term, we'll come back to this and play with this a little bit more. And what you can do is, if you look at this, so generally what you do with a planetary gears, they don't take up a lot of room. They spread out the load on more teeths. It's symmetrical. So there's a lot of advantages to planetary gears, or which are basically spur gears but arranged in this way. And so you might, for instance, hold the ring stationary. So now if you drive this center gear, then this carrier will move around. And what I'd like you to do is take a shot at seeing if you can figure out this question right here. So if the ring gear is held stationary, what is the ratio of the sun speed to the carrier speed? So again, here's the sun is in the middle. So if the sun has some certain speed, how does that relate to the carrier speed? The carrier is this piece right here that holds the planet gears. So you can reason this through, and let's see if you can do this. So there'll be these three survey questions that you should try to answer before class on Thursday. And yeah, so hope you have a great night.